Imagine a tool so insanely powerful that it literally dictates the fabric of reality. It bends space, shapes everything we see, and sets the absolute speed limit for the entire universe. Welcome to this explainer. Today we are taking on a pretty high-stakes mission, learning to manipulate this cosmic tool. Yep, we're talking about light. We are totally ditching the dry, boring textbook readings today. Instead, we're going to decode the actual physics of reflection and refraction so completely that you won't just memorize it, you'll understand it. By the end of this, you are going to be fully armed and ready to score a perfect 100% on your board exams. Let's do this.
3 times 10 to the power of 8 meters per second. Take a second to just wrap your head around that. That is the exact speed of light racing through a vacuum. Now ask yourself, what actually makes the invisible visible? The exact moment light floods into a room, bouncing off objects and transmitting directly into our eyes, that is when our reality is constructed. And honestly, the most fascinating part of all of this? It's all bound by incredibly strict, unbreakable mathematical rules.
So let's jump right into section 1, the foundational rules of reflection. Let's break these laws down so they're super simple. Imagine you're firing a glowing laser right at a sleek metallic mirror. The first law dictates perfect symmetry here. Basically, the angle at which your laser strikes the mirror, which we call the angle of incidence, is exactly equal to the angle at which it bounces off. Makes sense, right? And the second law? It just states that your incoming laser ray, the outgoing reflected ray, and the imaginary perpendicular line right where they meet, which is called the normal, all exist perfectly flat on the exact same plane.
All right, moving on to section 2, mastering spherical mirrors. Things get really interesting when we bend that flat reflecting surface into an advanced optical tool. I mean, think about the flat plane mirror you look at every single morning. It's totally predictable, right? It just gives you a virtual identical image of yourself. But spherical mirrors, they possess these wild shape-shifting abilities. Think of a shiny metal spoon. If you look into the hollowed-out inward curving bowl of the spoon, you're actually looking into a concave mirror. But turn it around to the bulging outward backside and bam, you have a convex mirror. Suddenly, your reflection can be drastically magnified, totally shrunk down, or even flipped completely upside down.
Now, if you want the ultimate cheat code for drawing your ray diagrams in the exam, just look for the mathematical pattern hidden right here in this table. Notice how, as an object moves closer and closer to a concave mirror, going from infinity past the center of curvature to the focus, the real inverted image gets pushed further away and it grows larger. But then comes this brilliant final twist. If you push the object extremely close, past the focal point, the image suddenly flips right behind the mirror. It becomes virtual, erect, and highly enlarged. All of that complex geometric movement, it is perfectly captured in one elegant little equation. 1 over v plus 1 over u equals 1 over f. Here, v represents your image distance, u is your object distance, and f is your focal length. And if you need to know exactly how big or small that image gets, well, that is simply the magnification. It's just a neat little ratio of the image's height to the object's height. If you can master these formulas and carefully apply your Cartesian sign conventions, you will have total control over literally any optical setup they throw at you.
Okay, here comes section 3, refraction, otherwise known as the plot twist.
Seriously? Just when you think you've totally mastered how light bounces, physics throws a massive sci-fi plot twist our way. Whenever light travels obliquely from air into a solid transparent medium, like a glass slab, it actually changes its speed and bends. We call this refraction. Just follow the path here. The incident ray enters the glass and it bends towards the normal because it physically slows down. Then, as it exits back out into the air, it speeds right back up and bends away. The real magic here is that the emergent ray coming out the other side is perfectly parallel to the original incident ray, it's just been laterally shifted over a bit.
And just like with reflection, refraction has an ironclad mathematical rule. Please do not let Snell's law intimidate you. It is simply a reliable, constant rule for any specific pair of media. It just tells us that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is always a constant number. We call this constant the refractive index. Think of it as a measure of exactly how much a given material hits the brakes on the speed of light. Let's look at the number 2.42, for example. This is the absolute refractive index of a diamond. What that tells us is that light actually travels a staggering 2.42 times slower through a diamond than it does through the empty vacuum of space. That is wild, right? It's also powerful proof that optical density is completely different from mass density. A material can be highly optically dense, meaning it bends light severely without necessarily being physically heavy.
Let's shift gears to Section 4, decoding spherical lenses.
So, we are now shifting from bouncing light off mirrors to actually transmitting and bending it through lenses. Take a convex lens. It's bulging outward and thicker in the middle. This acts as a really powerful converging tool. It takes incoming parallel light rays and forces them all to cross at one single intense focal point. On the flip side, a concave lens is curved inward. It diverges the light, basically scattering the rays outward as if they originated from a virtual point right behind the lens. Like I said earlier, these are literal mechanisms for controlling reality.
Now pay attention, because there's an absolutely critical difference between the math of mirrors and the math of lenses that you just have to lock into your memory right now. The mirror formula uses a plus sign, 1 over v plus 1 over u, but the lens formula, it uses a minus sign, 1 over v minus 1 over u equals 1 over f. Honestly, just memorizing that single, easily missed minus sign is going to save you countless marks. It is the absolute #1 place where mistakes are made on test day.
Lenses dictate how we interact with the everyday world around us. Think of a watchmaker using a tiny magnifying glass to see gears, or even just the spectacles you or your friends might wear. The actual strength of that lens is called its power, and mathematically it is simply the reciprocal of its focal length. We measure this power in a unit called diopters. So the shorter the focal length, the stronger the bend of the light, which means you get a higher, more powerful diopter rating.
Finally, we've reached Section 5, your board exam winning strategy.
All right, consider this your ultimate tactical breakdown. Pay really close attention to the top 3 fatal errors students make every year. Mistake number 1, completely messing up the Cartesian sign conventions. Remember, the object is literally always placed to the left of the mirror or lens, which means your object distance, u, is always negative. Mistake 2, confusing the nature of images. Just drill this in. Real images are always inverted, while virtual images are always erect. And mistake number 3, forgetting the easiest rule of them all. Any ray of light passing directly through the optical center of a lens does not deviate at all. It just passes perfectly straight through.
So we've decoded the math, the rules of reflection, and the strict laws of refraction. You now hold the exact blueprint for how the most powerful tool in the universe operates. If light literally shapes our entire reality, how will you bend it to master your exam? All the concepts are right here in your grasp. Step into that exam hall and show them exactly what you know. Keep reviewing these slides, and I'll catch you in the next explainer.